So today I'm going to be showing you how to calculate the density of a floating log just by knowing the radius of the log and how much of it is sticking out of the water. So we're going to be working with the concept of buoyancy, and simply put, buoyancy is the weight of the fluid displaced. And I'll explain that here in a second. So we're going to say we have some log here represented by this cylinder, and it's floating in the water, and this line right here is going to be representative of our water level. So everything that's below this line is submerged in the water. Now this log is going to have some length, L, it's going to have some radius, R, and this part here that's sticking out of the water, that height is going to be represented by a small h. Also, the area of the face of the log that is under the water is going to be represented by capital A. So this A does not represent the full circular face of the log, it just represents the area of it that is underwater. So like I said, we're going to be finding the density of this log. So we're going to be finding the specific gravity in terms of h over r. So just by knowing h over r, you're going to be able to find the specific gravity or density of this log. So, like I said with buoyancy, the weight of the log, the entire log, has to be equal to the weight of the water that it displaced. So the water that originally existed here. So the weight of this log is going to be equal to the density of the log times the volume of the log. And that volume is pi r squared times the length times the gravitational constant g, which is equal to the density of the water it displaced times the volume of that water, which is A, times L, times gravitational constant g. Now we see that both sides of this equation factor in the length of the log and g, so we can just go ahead and cross those out, leaving us with the density of the log times pi r squared has to be equal to the density of the fluid, in this case water, times that area A. So I went ahead and moved to a fresh sheet of paper here because there's quite a bit of side calculations we have to do. So what we need to do now is we need to find an expression for that area A, everything that is underneath the water level on the face of the log, in terms of R and H. So I'm going to redraw the face of our log here. This is going to be our water level. And I'm going to go to the center, and I'm going to draw 3 radii. 2 that go to the points where the water level touches the edge of the face of the log, and 1 that goes vertically. So like I said, they're all 3 radii, so we're going to mark these 2 with R. We know that this length here is h, the part that's sticking out of the water, meaning this length right here must be equal to r minus h. I'm going to go ahead and write that in. We're going to say that this angle here is equal to theta. We're going to say that each of these 2 lengths here, 1, 2, are equal to x. So, like I said, we need to find this area of everything underneath the water level in terms of r and h. And the way we're going to do that is we're going to find the area of some of these smaller pieces that we split it up into, and we're going to subtract them. So first off, we want to find the area of this triangle right here, this large triangle that we split in 2. And so we know that the squares of the 2 legs added together have to equal the square of the hypotenuse r. So I'm going to go ahead and write that out. We got r minus h squared plus x squared has to be equal to the hypotenuse squared, which is r. I'm going to expand this term here. So if r squared minus 2hr plus h squared plus x squared is equal to r squared. Now we have an r squared on both sides. I'm going to go ahead and cross those out, which leaves us with x squared is equal to 2hr minus h squared. So because we're just solving for x, we're going to take the square root of both of these sides. So we know that x equals the square root of 2hr minus h squared. So to find the area of this large triangle, we're going to take the area of both these small triangles and add them together. So the area of one of these small triangles is 1/2 times base, which is x, which we just calculated as the square root of 2hr minus h squared, times height, which we know is r minus h. And we have to multiply by 2 because we're adding the two of these small triangles together. So the 2 and the 1/2 are going to cancel out, which leaves us with the area of this large triangle here is equal to the square root of 2hr minus h squared times r minus h. So now we have the area of that triangle. Now we want to find the area of this piece of pie looking shape here. So we know that that area can be represented by two times this angle theta, so this large angle here, over 2 pi times the area of the whole circle, which is pi r squared. Like I said, we want everything in terms of h and r, so we need to find an expression for theta in terms of h and r. So we know that cosine of theta has to be equal to the adjacent over the hypotenuse, in our case, r minus h over r. So I'm going to go over to the side and write this. Theta equals cosine of theta is going to equal r minus h over r. Since we're solving for theta, theta must equal the arc cosine of r minus h over r. So now we can plug that directly into that. So we have the area of that piece of pie is equal to 2 times the arc cosine of r minus h over r over 2 pi times pi r squared. And we see we have a pi on the top and bottom, and we have a 2 on the top and bottom. So the area of the pie shape is equal to arc cosine of r minus h over r times r squared. So we want to find this area of everything that is above the water level. So in order to do that, we're just going to take the area of the pie that we found and subtract the area of the triangle. And we have both of those, so I'm going to go ahead and just write that out. So we have the area of the pie, which is the arc cosine of r minus h over r times r squared minus the area of the triangle, which is the square root of 2hr minus h squared times the quantity r minus h. So that's what that small area is equal to. But we want to find the area of everything underneath, because that is what A represents. So we're going to take the entire area of the circle and subtract that small sliver above the water level. So in all, that section, which is A, is equal to pi r squared minus the arc cosine of r minus h over r times r squared plus square root of 2hr minus h squared times r minus h. Okay, so now we're going to combine our two previous steps together to come up with a final equation. So I'm going to start off with the original formula we came up with, which is the density of the log times pi r squared is equal to the density of the water times that submerged area A. So now we have an expression for a in terms of all r's and h's that we can go ahead and plug directly in where a is. So I'm going to go ahead and do that now. We got the density of the log times pi r squared equals the density of the water times that expression we just came up with, which is pi r squared times the r cosine of r minus h over r times r squared plus the square root of 2hr minus h squared times the quantity r minus h. So now what we're going to do is we are going to divide the density of water over to this side here, and we're going to divide pi r squared over to this side, so it's going to have to be divided by each of our three terms here. So let's go ahead and do that. So on this side, we've got the density of the log divided by the density of the water equals each of our three terms divided by pi r squared. So we have our pi r squared term, we have our cosine term, finally we have our square root term. And you'll see that a couple of things can already cancel out here. I mean, we got pi r squared over pi r squared, which is the same thing as 1. We have an r squared on the top and bottom here, and nothing's going to cancel out just yet here. So let's rewrite this. Now you'll see we have a density of our log over our density of the water, and any density of an object divided by density of water is also known as specific gravity. So we're going to go ahead and represent this term here as SG for specific gravity. So we have our 1 minus our cosine term, it's cosine of r minus h over r, times 1 over pi, because we divided that by pi, plus 1 over pi r squared, because nothing canceled out here, times radical 2hr minus h squared times r minus h. So now the next thing we're going to want to do here is manipulate some of these terms in order to get them in terms of h over r, as I previously addressed at the beginning of the problem. They already are in just terms of h and r, but we want them in terms of h divided by r. So we're going to manipulate some of these terms here. The first part of this is just going to be rewritten a lot because most of the manipulation comes towards the end. So here, we're going to divide everything, or we're going to multiply everything under this radical by r squared over r squared, which is just multiplying it by 1. And we're going to multiply this r minus h term by an r over r, which is once again the same thing. Now, let's go ahead and rewrite this again. We'll do some more canceling in this next step. Got a cosine term. And you'll see that we have an r squared under the radical here, so we can go ahead and write that outside of the radical as just a normal r, not r squared. So inside the radical now we have a 2hr minus h squared, and all that is divided by r squared still, times r minus h times r divided by r. So we have an r squared in our denominator here, and that can go ahead and be canceled with this r that's in the numerator of this term, and this r that's in the numerator of this term. So we're going to go ahead and rewrite this. We are getting close to our end here, so not too much rewriting to go. We're going to go ahead and divide each of these two terms under the radical separately by r squared, because that lets us do a little bit more cancellation. Rewrite it again. And so we're going to go ahead and cancel this r here and one of the r's in the bottom, giving us 2h over r minus, and then we have an h squared over an r squared here. So I'm going to go ahead and write that as an h over r, all of that squared. Oh, hold on. My mistake. Since we canceled that r up there, we actually don't need it in these two terms down here. I accidentally rewrote it. So now we are almost done. The last thing that we have to do is, you'll see we have an r minus h over r twice in our equation. And I'm going to go off to the side here and write this out. R minus h over r is the same thing as r minus h over r. And r minus r is the same thing as 1. So that is the same thing as 1 over h minus r. So we can go ahead and replace both instances of that r minus h over r with this new 1 minus h over r term. So this should be our last rewrite we have to do before we are done. Oops. To multiplication. Okay, so our final expression here is standard gravity is equal to 1 minus 1 over pi times arc cosine of 1 minus h over r plus 1 over pi times the square root of 2h over r minus h over r squared times 1 minus h over r.
Okay, so that equation that we just came up with is good if you know your h over r ratio and you're trying to find specific gravity, but I'm going to show you a short Python script that can be used if you actually know your specific gravity and you're trying to find your h over r ratio. So the first thing we're going to want to do is we're going to want to import the NumPy library to have access to some functions that we're going to need in our program. And we're abbreviating that as NP. So any function that we use from this NumPy library is going to begin with an NP dot, which you'll see later. Next up, we want to import the function root scalar, and that comes from the Skippy or Skypy.optimize library. And I will show you where we use that later in our program, and that's going to help us be able to find the roots of a scalar function. So that's the first part of our code. The next thing we're going to want to do is define our variables. So the first one is going to be our h over r ratio. And what we're going to do here is use one of our NumPy functions, which is np.linspace. And you'll see we're going to do this from 0 to 1 with 10 numbers in between. So basically what this does is it creates a matrix from 0 to 1 and includes 10 numbers that are evenly spaced apart. Next, we're going to want to define our specific gravity equation, and I'm going to pop that up here on the screen just to remind us what that is. That is that equation that we just solved in the first part of the video. And that's going to be 1 minus, and here's one of our NumPy function. It's arc cosine of 1 minus HR. That's going to be subtracted by another one of our NumPy functions, which is np.square root. That's going to be the square root of 2 times HR minus HR squared. And multiply that by the quantity 1 minus HR. And that is all going to be divided by pi. And pi, instead of just being able to type pi, it's actually another NumPy function, so it's going to be np.pi. So that is all for our second part of the code. So we've imported some of the functions we needed in the first part, In the second part, we defined some of our variables. So now we're going to define another function, which is, whoops, that was a wrong parentheses, the function f of hr. And in this function is going to return a value for our specific gravity function. So I'm just going to grab that, put it in here. And we're going to subtract some value from it. So the reason we are subtracting some value is if you picture a graph where specific gravity is graphed against your h over r ratio, and specific gravity is your y-axis, and your h over r ratio is your x-axis, if you move that graph down, you're going to be able to solve the root for wherever that value crosses the x-axis. So if we make this 0.8, for example, then we'll be able to solve what the HR ratio is whenever specific gravity is 0.8. So we're done defining that function. And the last thing we're going to do is define the variable result. And what result is going to be is the result of what happens if you run the root scalar function, which we called earlier, on that f function we just defined. Okay, and the last thing our program is going to do is going to return what the result is. So we're going to run all three of these chunks in order, and our function, our program did work. So as you can see, if we know that our specific gravity is 0.8, we can see that the root that it solved for, or the HR ratio, when specific gravity is 0.8, is around 0.51. So let's say we were to use a specific gravity of 0.6. You could conclude that your HR ratio would probably increase because the less dense your log is, the more of it that will be sticking out of the water, which will give you a greater value for H, which would make your HR ratio higher. So we're going to run this again using 0.6 as our specific gravity and see if we get a root that is greater than 0.51. So let's run this again. And we can see that, in fact, the HR ratio for a specific gravity of 0.6 is higher than a specific gravity of 0.8, which is around 0.84, showing that more of the log is sticking out of the water if the log is less dense.